Welcome everyone to our first webinar in June. Thank you for being here with us. We are going to talk today about simplifying machine learning for fNIRS, implementation and benchmarking with BenchNIRS, with Johann Beneradi. We are NIRx. We are a company deeply passionate about science. We love to take not only our devices further, but also the whole fNIRS community. And I guess that's the idea of the webinars, and this webinar in particular, where Johann will talk about some best practice on evaluating models and applying machine learning to fNIRS. And we're all very curious about that. If you want to talk to us and connect to us, please see all our social medias and send an email to our consulting@nirx.net address. We'll be happy to take any questions and understand more about your research. We also have a newsletter where you can get this nice QR code there, and where you will learn more about new features, about new things that we are doing, and the next conference that you can find us. On some of the considerations, so you're all muted. Questions are welcome at any time. The content will be available in our website. And again, if you have any further questions, please write to our consulting or support email. Without any further ado, forgot about important people as well here. Myself as a moderator, and our dear colleague Kami, that is on the background doing all this for us. Without further ado, we have done here Johann Beneradi, research in neuroinformatics at the University of Cambridge, currently working with the Brain Imaging Global Health Project. He has obtained his PhD in computer science from the University of Nottingham, and his research focuses in neuroimage data analysis and machine learning for fNIRS, with applications ranging from study of neurodevelopment to brain-computer interfaces. It's a pleasure to have you here, Johann. The floor is yours.
Thank you very much. Thank you for the kind introduction, and thanks everyone for joining. So I'll just share my screen. And hopefully that all works well now. Right, so yeah, today I need to talk about simplifying machine learning for fNIRS. But before we start, I wanted to acknowledge the contribution of my colleagues who are awesome, and so that's colleagues that were involved in this work from the University of Nottingham. So Jeremy, Alexandra, Michelle, Max, but also from Cambridge, so Borja and Catherine. So thank you to them for being collaborators on this project. And yeah, so let's dive straight into it, starting with a little bit of background. Well, I assume since you all know NIRx now, you may all know that what fNIRS is, but here's just a slide to kind of recap roughly what it is. So yeah, a neuroimaging technique based on optics that enables to measure the brain activity. But in this case, so what will interest us, so in the case of this study is really that in the end, what we'll have with it is time series signals. So oxyhemoglobin and deoxyhemoglobin time series, so multiple channels over time. And usually what we want to do when we do machine learning for fNIRS, it may be for various applications, such as, for example, brain-computer interfaces. But what we'll do is typically take a segment of the data over a couple of seconds, and the goal would be to kind of predict what does this correspond to. So, for example, if a user is wearing the fNIRS device, what was, for example, the user's cognitive state, or what was the user thinking about? And that's what we're trying to predict from the fNIRS signal. So more specifically, a bit of background about machine learning. So I guess all of us, we probably hear a lot of terms around AI and machine learning, but here I just wanted to kind of make clear what is what. So let's first start with artificial intelligence. I guess it's like a very large term to define pretty much anything in which I guess a computer can be considered as smart. It's quite vague, but here we'll talk more specifically about machine learning, which is more precisely defined. And here, so we'll take the definition as this is a set of techniques that enable a computer to learn from examples. So yeah, very data-driven. A subset of machine learning is called deep learning. So that has made a lot of noise lately with the recent advances in AI. But what it is, it's a subset of machine learning, and it consists in models that are neural networks with multiple layers. So now when we do machine learning, there's different types of machine learning that we can do. And here I wanted to describe the two most common ones, which are supervised and unsupervised learning. There's also other types such as reinforcement learning, but we'll not dive into this here. But supervised learning, what it is so since our model is learning from example, in the supervised machine learning, we have each example, so each data point that we provide to the model has a label associated to it. So that will enable to learn this way, as opposed to unsupervised learning in which the examples don't have labels associated to it. So that can be for different goals, for example, just like learning how to cluster the data together or this kind of things. But here we'll focus more specifically on supervised learning. And finally, one term that is very important that I wanted to kind of define here is whenever we have machine learning models that we learn from examples, so how they will do that is they will have some internal parameters that will be able to be adjusted using the examples. As opposed to those internal parameters, we have also very often on machine learning models what is called hyperparameters. And those are parameters that are external to the models, and they're essentially set by the experimenter, the researcher, and they can, for example, control the learning of the model as opposed to actually learning something. So they control how fast we can learn, all these kind of things. So this may seem to be abstract. So here's a little example. So let's take in this case a neural network, which is a very simple artificial neural network. So that's neurons that are connected to each other. And here in this case, we have 4 layers. So how does this work? So what we'll do is feed a data point, so an example, to the model. So in this case, from left to right. So that's called the forward pass. So from this data example, the model would kind of process it and then output a result. And this result initially would be quite random. And what we'll do is essentially compare whatever was outputted with the actual label that we had in the case of supervised learning. So for example, whenever we do classification, we want to know, if we feed an example, what class it is. So the model will output a probability distribution for each class, and we will know what class it is. So from that, we can compute what error between the probability distribution predicted versus the actual expected things that we were supposed to have. And from that error, what we can do is then update the weights of the connections between the neurons in the model, and in order to reduce the error. And then we'll then repeat that many, many times. So we feed another example, compute the error, and then update the weights, and do this many, many, many times on many examples. So that's essentially how a neural network works. And in this case, example of hyperparameters can include the learning rate, for example. So as opposed to the weights of the models, in this case, which would actually be the internal parameters, here we have the external parameters, which is, for example, the learning rate, how much the weights are updated after each iteration. Another one could be the mini batch size. this is how many data points do we feed at once. So in this simple initial example, I explained we feed one example, but eventually we can feed many examples, then compute the error, and then update the weights. So that would be the mini batch size. How many examples do you feed at once? And then another one could be the number of epochs. That's how many times you would iterate over the whole data set. So when you have a whole data set, you can, for example, feed each point one at a time, and then you would do that multiple times over the data set. So you pass once over the data set and second time and so on. So that's the number of epochs. So hopefully that can give you a better idea of what we mean by hyperparameters. So now, whenever we have like a goal in which we want to use machine learning, so for example, in this case, there would be classification of fNIRS data. So the goal would be really what the question we want to answer is actually how well can we predict the class of unseen data? Because obviously we have some training data in order to train the model, but then we want to take the model and use it in order to predict the class of new examples. So how it's typically done is whenever we have a data set, in order to be able to answer this question, what we'll do is split the data sets, and it's called the training test set paradigm. So that essentially consists in extracting, like splitting the data set and keeping one part for testing. And then we can train the model on the remaining data. So now, as I talked about the hyperparameter, in order to be able to know then what hyperparameters should I use for my model training, we can do the same process on the remaining data. So we can split this further to extract a validation set. And every time we will train a model with a set of hyperparameters on the training set, evaluate it on the validation set, and we can do that for many different sets of hyperparameters, and that would enable to compute the best performance on the validation set. Once we have this, then we can evaluate on the actual unseen data, which is the test data, and that would give us the evaluation performance of the model. So, right, so what are the challenges with this? So with machine learning in many different fields, actually, there may be some issues, actually, and that's actually something that has a quite great extent, in fact. And that's what we call the leakage and reproducibility crisis. So this article is actually an awesome article, and it's doing kind of like a compilation of all the flaws and issues that there are in published works in many different scientific fields using machine learning. So I highly recommend to read that paper. Maybe not before sleeping, because you may do some nightmares, but because it's a bit scary. But yeah, so that's actually a very extensive issue in machine learning, and the fNIRS field is not exempt to that issue. So with our team, we kind of try to identify challenges that like current limitations that we've seen in machine learning for fNIRS, and that essentially consists in like lack of details or lack of robustness in some approaches. So we kind of categorize this in two different categories. So first, the methodology, and that can consist in how you use your data in order to select hyperparameters and evaluate. So the training, validation, test split. That can also be just like very basic data leakage, in which you have actual examples that we're supposed to use for evaluating your model that end up like you end up training your model on some of those examples, which is a clear leakage. But also some issues related to how the hyperparameters are selected, or what metrics are used, or like how statistical tests are used in order to kind of claim that a model is better than another one. And finally, the second category is related to the reporting of how machine learning is done with fNIRS. And again, that is related to lack of explanation on how like the methodology is applied in order to evaluate the models, or less lack of information as to like what is the actual inputs of the model in terms of its shape or the number of example per class, for example. And also just like what hyperparameters have been tested, and even sometimes like what is actually chance level. So those are quite big issues because it makes the reproducibility quite often impossible. And eventually it could mean that in some cases there is some bias or over-optimistic results. And that's a bit of a problem if you want to evaluate a model on the truly like unseen data. So here I just want to give like a couple of concrete examples on how we could eventually make these flaws happen. So first scenario, we'll call this like misleading metrics. So here we'll take the simple goal, which is trying to classify let's say a cognitive state from a single trial fNIRS segment. So we have fNIRS data and we're trying to predict what class does it belong to. And so we have classes in our example. Let's say we have classes that are not balanced in the data set. So that means that there is much more examples in one class than other classes. For example, that can be due to trial rejection based on, for example, motion artifacts. And let's assume in this case, we use the accuracy as a metric of interest in order to evaluate a model, or machine learning model. So this is a problem because it can lead to the overestimation of the usefulness of the model. And what I mean by that is that if most examples end up belonging to a specific class, let's say we have 90% of our examples in the dataset that are in one class and 5% in another class, if we have a very dummy classifiers that we classify that most common class all the time, it would appear that we have an actual very high performance as measured by accuracy, essentially 90% in this case. However, it would be in fact quite useless because it wouldn't generalize well in different cases. A second example, we'll call this the normalization leakage. So for example, here, exact same goal, we're doing single trial classification from fNIRS data. And here what we'll do is normalization of the data with, for example, min-max scaling. So across the whole data set, essentially, we have the recordings that are time series, like amplitude time series. What we want to do is like squash everything between 0 and 1. And we do this essentially computing the minimum and maximum on the whole data set before actually splitting between training, validation, and test set. So this is an issue because it can overestimate the generalization capabilities. And this is simply because if we see eventually the test data, to make an informed decision about like what is the minimum and maximum, actually we're not reflecting the performance of unseen data anymore. Because we've seen this data in order to select the minimum and maximum. And finally, I wanted to talk about a last example, which we'll call optimized leakage. And that's probably one of the most common issues that we can encounter. And this exact same goal here, single trial classification from fNIRS data. And here, this issue will really be related to the hyperparameters. So in this case, we do a training test split only. So just split the data and extract the test set, and then have the remaining data for training the model. And in this case, the model is trained on the training set, and the hyperparameters are selected based on the performance on the test set. So every time we train a model with a different set of hyperparameters and see what's the performance on the test set. And then select the hyperparameters based on that. And this is a very big problem because it may very likely overestimate the generalization capabilities of the model. And this is because the test set in this example is in fact used to make an informed decision about what hyperparameters we'll use. So that's essentially a flawed methodology because at this point, we're no longer assessing the model on unseen data, which is what we're interested in the end. So here you may start to kind of see how it's easy to kind of miss something and have like the evaluation actually be somehow flawed. And the idea is that we had is to kind of build a tool in order to make it easier to like use machine learning models for fNIRS data without worrying too much about potential issues and like leakage issues. So that's why we built BenchNIRS, which goal is to essentially simplify machine learning with fNIRS. So it's an open source Python package, and it enables a couple of things. So here is just a summary. So you can load open access datasets. You can do some signal processing and extract some features from the fNIRS data. You can train, fine-tune, so like select hyperparameters and evaluate machine learning models. And you can also produce different like figures and graphs that are useful for you to kind of develop new machine learning models. So, and finally, it enables to do benchmarking and comparison of machine learning models against each other. So let me enter a bit more in the detail. So when it comes to the data sets, so at the moment, that's the data sets that are supported natively in the loaders of BenchNIRS, but hopefully we can add more. And eventually, you can also use your own custom data set with a little bit of code, but this is really the data sets that are built in so that it's very easy to load them. So yeah, we have 5 of them that are open access. So 2 of them are based on n-back tasks. So with 3 classes. Then we have data sets word generation versus REST. So 2 classes. Another one of 2 classes with mental arithmetic versus REST. And a third and last data set of 3 classes, which is right hand finger tapping or left hand finger tapping or foot tapping. So actually that last data set was used to kind of have a bit of a reference because these finger tapping tasks are usually quite common in order to just validate any fNIRS system. That's usually a task in which you have very clear responses. So that's why we also included this. And so then with those or any data sets that you can also load eventually manually in Python, so you will be able to do some signal processing, and this relies on 2 libraries, so NIRS Simple and mNE. So mNE is an awesome library that initially started for EEG and MEG, and since a couple of years now is supporting also fNIRS, thanks to the awesome work from Rob Luke and many other people. But yeah, so the signal processing you can do with it is the conversion of raw signals into hemoglobin concentration changes with the modified Bernard-Baird law. You can filter and correct motion artifacts. You can epoch the data, so split it into segments, and that includes using baseline correction to kind of bring them back to the 0 axis. You can also combine channels by region of interest. And eventually, since it's based on mNE, you can actually use any kind of signal processing that mNE enables to do on the data. So yeah, there's really a lot more that you can eventually do. So second, we can do some feature extraction. So that involves, at the moment, doing the mean over a specific period of time of the waveforms, or computing the standard deviation over time, or the slope of the linear regression. And finally, the core of the thing is really training machine learning models. So that includes traditional machine learning models, and that's based on scikit-learn, but also deep learning models, and that's based on PyTorch. And then, so the core, like the cornerstone of BenchNIRS is really to enable you to train, fine-tune, and evaluate the models in a reliable way and very easily. And that brings us back to this diagram that I showed before, in which we were using a training set to train the model, the validation set to select the hyperparameters, and test set to evaluate the model, so report the performance. Now, in this approach, if we split the data randomly, there's a problem, which is that the results may vary greatly depending on how you split the data. So, for example, whatever data will be used as a test set may be like very random. So you may end up on a bit of data which is very bad for evaluating your specific model, or actually maybe very favorable, in which case you would seem to have high results, but high performance, but actually on other data it would be much less. So in order to solve this problem, there's a very common approach that is called k-fold cross-validation. And what it consists in is essentially, so you have your whole data set, and what you do is split this data set into k-folds. So in this case, we have 6 of them, so it's 6-fold cross-validation. And what we'll do is keep one of them for the testing of the model, so the evaluation of the model, and we can train the model on the 5 remaining folds. And then what we'll do is do this in a loop, taking each fold as a test set at one point. So every time we take one test set, we train the model on the remaining, and so on. And now you may ask, so what about the validation set? So that's where nested cross-validation comes in. So you may have kind of guessed the intuition of it now, but essentially you will do cross-validation within a cross-validation. So first, for example, you extract your test set, and then on whatever remaining, you will take like one of the folds in order to do the validation. And every line, we will train the model and validate it. That will enable us to try different hyperparameters every time and select the best ones. And then finally, once we found the best hyperparameters, we can then evaluate the model on the test set. And so in this case, the inner cross-validation will be used to fine-tune the hyperparameters on validation sets, and the outer cross-validation is used to evaluate models on test sets. And so if we continue this with the outer cross-validation, so every time we change our test sets and we do the inner cross-validation again, so for each of the outer cross-validation iterations, so like so. So why is it good? It has a couple of advantages, and that's very useful in the case where we have small data sets. And that's very often the case in neuroimaging data in terms of number of like sample size, essentially. And this is to kind of put in comparison to other fields that use machine learning very commonly, such as computer vision or like text, in which they have millions and millions of images or millions of text in order to train their models. Here, with neuroimaging data, we have much less, and specifically with fNIRS, there's even very often less data. So this approach comes in very handy. And this is because we can use the data more efficiently, because we will like at some point pass over the whole data set in order to evaluate the model, and this will be done in a way that is not actually seeing the data, like the evaluation data, because each model training is independent from each other. So we can then compute the performance on each selected test set and do the average, and that enables to estimate the performance more reliably. And then third point is that it gives also an indication of the model robustness. So using, for example, how much variability there is between the different evaluations that we will do on the outer cross-validation, for example, we will be able to tell if it's varying a lot, like is our model very robust to kind of different data, or is it performing poorly? So disadvantages, the main one is that it will be more time consuming than just to one random training, validation, and test set split. But as we have small data sets with fNIRS, actually the advantages will very greatly outweigh the disadvantages. And for example, the issue of randomness in the data will be much more pronounced when we have small data sets, as opposed to if we have very large data sets, for example, with computer vision. If we take like 20% of a large computer vision data set, it will still be thousands and thousands of images, which will hopefully make it less random. With fNIRS, when we take 20% of the data, then it would be much less and much more subject to randomness. So yeah, in the case of small data sets, we believe that the advantages greatly outweighs the disadvantages. So that's really the cornerstone, and it enables you to do this whole process using the Python package. But also you have a lot of utilities for model development and troubleshooting. So that includes, for example, training graphs, this first graph, first figure, for example, or like different metrics. So for example, you can have confusion matrices that will give you an indication of how well your model is predicting each of the classes you have. And then you can have like actual metrics like accuracy, but other as well, which may be more relevant in the case where you have unbalanced classes, such as the precision, the recall, or the F1 score. And you can also produce evaluation figures to kind of compare models to each other. And you can also compute some stats to compare models to each other, and also to compare models to chance level, for example. So how does it look like? So if you use the Python package, so what you have to do in order to install it, so you have to install it with pip. So that's a package manager. So you do a pip install BenchNIRS, which is the name of the package. And then from this point, you will just have to import the package. So that's the first line here. And then we have essentially one line to load one of the open access datasets. For example, in this case, the motor execution dataset of finger tapping, specifying the path of wherever we saved it. Then we have one line to process the epochs. So that will essentially like extract the different segments with the associated label, because here in this case, for example, we want to do supervised classification. And then we have one line in order to train, fine-tune, and evaluate the model, and that will return results. So here, my model would be like, for example, any deep like PyTorch model that you may have defined. You would just input this in the function, and it will automatically train it, fine-tune it, and return you some results as well as figures. So this package is provided with the documentation that is online. We really like documented all the functions, what inputs and what outputs did they have. And we also provide a bunch of examples, and that includes some examples that we've published in a benchmarking that we've done. So here you can access the documentation at this page. And in a short while, I will do an actual demonstration on how to use the framework. But first, what I wanted to do is show you a bit of the results that we had. So actually using the BenchNIRS package in order to perform a benchmarking of many machine learning models on many open access datasets and with different approaches. So what we've done is using BenchNIRS in order to benchmark 6 different machine learning models. So that's linear discriminant analysis, super-vector classifier, and k-nearest neighbors as part of the kind of traditional machine learning models, but also some neural network-based models, such as the artificial neural network, which is the standard one that I've explained earlier, but also convolutional neural network and long short-term memory. So we've So we've kind of benchmarked those models on all the datasets supported by the framework. And we also investigated factors that we were thinking may influence the performance. So that includes the dataset size that we varied for each dataset, the epoch duration, so window size of each trial that we presented from the trigger onset, the epoching method, so like epoching, like getting the segments from the trigger onset or just having a smaller window that would slide over the whole data. And also studying different generalization goals. So for example, classifying on data from completely unseen subjects, as opposed to classifying, like building a classifier for each subject independently. So here is an example of figures that we have in the paper. And that's something that you can get with the framework. So for all the models and all the data sets, and in this case, in the case of unseen subject classification. And so here is the kind of table of the actual results with indication on the significance compared to chance level. But I guess the first thing that we can notice is that overall the performances are quite low. And initially, so what we wanted to do is kind of provide basic models. I mean, like different architectures and see how they compare to each other initially. And yeah, we see that the models are quite low actually, and that the models are have quite similar performances, except maybe the linear discriminant analysis that performs quite, I mean, that performs significantly greater than chance level for every dataset that it has been trained on. Also, one thing that we notice is that the motor execution dataset, so finger tapping, had unable to get high performances compared to the other dataset, and that's kind of what we predicted initially, as this task is very common. So I don't want to spend too much time like just dropping results and results. If you're interested in this benchmarking, I invite you to have a look at our paper that was published last year. But also the scripts can be found in the examples of the framework. So every script that we've used in order to run the benchmarks can be found on the documentation. But just kind of like highlights of what we found. So I guess the first model is that there's no model that consistently stands out, regardless of the methods or the generalization goal, except maybe like linear discriminant analysis that, despite its simplicity, because that's actually a very simple traditional machine learning model, that model was quite robust, like across like all data sets. Second point is that classification is easier on some tasks than others. So that's what I've said just earlier with the finger tapping task, for example. Third is that the dataset size at the scale of the dataset that we had, keep in mind that the biggest dataset was 30 subjects. It did not have much influence, so at that scale, but maybe we can hypothesize that if we like build much larger datasets at some point, eventually, like deep learning models may perform better, but are still open to like research. And finally, that models with feature extractions. So we we trained some models using as inputs some features extracted, so that includes the mean, standard deviation, and slope of the linear regression. They benefited from longer trial durations. So as we increased the segment duration, the performance increased. So yeah, along with these benchmarks and our experience of developing the framework, we kind of came up with like a list of recommendations, like suggestions that we want to provide to kind of in the hope to help people who want to use machine learning with fNIRS. And so these suggestions we also did them into methodology and reporting. So first, when it comes to the methodology, I guess the first thing that is kind of like a prerequisite for like doing machine learning on one data set is the goal, like the classification goal that you're trying to achieve, is adequate with the experimental design. And that includes considerations such as, like, for example, the order of trials, in order to be sure that if you train a model on one data set, it will well generalize on other data sets that may be collected somehow a bit differently. For example, to avoid order effects or learning effects or these kind of things. Second is the training validation test set split adequate with the generalization goal? And that has really to do with whatever you want to build a model that would be able to classify on unseen subjects, or for example, within subjects, or also like unseen session. So this kind of considerations. The third one is, has nested cross-validation been used? So yeah, this is really like an approach that makes the results much more stronger in terms of the confidence you can have. And that's really useful in order to have more confidence in the results and that they would generalize better. And that includes, for example, has the hyperparameter selection been performed, so on the validation sets only, and have the test sets been used only for evaluation, so no hyperparameter selection. Sixth point is, has it been ensured that the test sets were not included for the normalization? And that's what relates to the example that we've described at the beginning. Another one is, has it been ensured that there was no overlap between training, validation, and test sets? So that may sound obvious, but that's something that may be easy to miss whenever, for example, you use sliding window over the whole like data, and those windows may have some overlapping between each other. So you may want to make sure that there's no overlapping windows that are in different sets, for example. And then have the appropriate metrics been used, depending on what depending on the data set you have and what goal you're trying to achieve. So that includes the issue related to accuracy, as we've explained earlier, which may not always be the best metric. And finally, has a statistical analysis been performed whenever we want to claim that a model is better than another one, or is just significantly greater than, like, performing significantly better than chance level. And the second type is about reporting. So the first one is, have the number of classes and chance level being clearly stated. So that's always useful to have. Then have the inputs of the models been described. So that includes the shape and the number of examples per class. Has the cross-validation implementation been described, again, related to the generalization goal? Has hyperparameter selection been described? So for example, what method did you use, and like what actual hyperparameters were tested in that selection process? Have every detail of each model been provided? So that includes essentially all the details in order for someone else to reproduce the results. So for example, the architecture, the hyperparameters, etc. And then finally, like if a statistical analysis is performed, have the test been described, the assumptions been verified, and so on. So you can find this checklist in the documentation of BenchNIRS again. And this is really kind of like a suggestions, but we really encourage you, if you have any feedback on it, to just let us know, and hopefully in the hope to kind of make this checklist more useful to more people and just make it, yeah, just better, essentially. Right, so now we are approaching the end of what I have to say, and I just wanted to kind of do a demo, like a short demo of the framework. So if you want to kind of use it by yourself, actually, so I've created a notebook that is hosted on Google Colab, and that means that you can if you access this link or by scanning this QR code, you will be able to access this notebook and run it for yourself. I think you just have to essentially copy it to your own Google Cloud. So I will paste the link in the chat, and hopefully everyone can see it and access it. And yeah, just a little disclaimer is that in this example, it's very simple. So obviously it's good for you if you want to kind of play with the framework and just see how it works, but do not use like the scripts as is for actual research or publication, because they're very simple and very limited. Right, so for myself, so if you access this, so you should end up on a page like this and be able to copy it to your own cloud and hopefully run it smoothly. For myself, I will just use a local copy just to avoid potential issues. Yeah, so I kind of walk you through the example here. But I've put up again the documentation and the examples as links if you want to have a look. Right, so let's start. So the first thing we'll do is actually install the package. So that can be done using pip. So in the framework, if you run this using this kind of exclamation mark command, that will do some kind of system command that will enable to install the library in the Google Colab environment. So personally, I have already installed it, so I will not do it again. And then what we'll do is actually import the package. So here we just import it, and for simplicity, we just import it as bn just to make it shorter to write later on. So here I will import it, and I just print the version just to have an idea of like what version are you actually using. So here in this case, 1.2.5. And then what we'll do is actually download one of the datasets. So that will be, in this case, the dataset from backend colleagues, which is the finger tapping, foot tapping dataset. And so, yeah, there's 3 different conditions. So left-hand finger tapping, right-hand finger tapping, and foot tapping. So in the Google Colab notebook, so you may have so I've put 2 commands in order to download the dataset directly from command line. This may or may not work, simply because in some cases, actually just for kind of website protection, you may be prevented from running too many times wget. So maybe if too many people run it at once, it may return a kind of error, but you will be always able to kind of download it manually at this address and then upload it in the Google Colab just by drag and drop. So these 2 lines will essentially download the dataset and unzip it into a folder that is named back 2019. So here you can see I have it here in my environment, and it consists in 30 files for the 30 subjects. And the first thing we'll do is load it with the load dataset function. So here we specify what dataset we want, what's the path, and we'll do some very basic signal processing here. So just a bandpass filter from 0.01, between 0.01 and 0.5 hertz with a motion artifact correction using temporal derivative distribution repair. And we will combine channels by region of interest in the area of interest, which in this case is the sensory motor cortex, since we're doing like hand finger tapping. So yeah, I'll just load this. So yeah, it's loading the subjects one after the other. And then, so what I do in this cell is also print whatever is returned. So in this case, you may realize that it's actually an many epochs object. So that means that you can do pretty much any many operations that you would do on that you would want to do. So any further signal processing or things like that. So here I print it in order to kind of see what's inside. So in this case, so we have 750 examples for each of the class. So that's right hand, left hand, finger tapping, and foot tapping. And then we have a bunch of unlabeled segments that we will actually not use here. So that's why here in this case I select the epochs just for left, right, and foot. And here what it will do is actually prepare the data for model training. So it's essentially building an array. So it's essentially returning a tuple of arrays, and that will essentially consist in NIRs, labels, and the subject's IDs. So if I want to print, for example, NIRs, I can see that, yeah, that's a NumPy array. Same for labels. So it's a bunch of like 0, 1, and 2 corresponding to the class here, the classes here. And then subject IDs. So yeah, it's like from 0 to 29. But here, for the sake of simplicity, we just keep it as like a tuple. So if I print it, it's essentially like importing like everything in one variable. And now we can use this data as inputs of our deep learning function. And what we'll do in this case is just use an LSTM model, so long short-term memory model. That is the one that we used for the actual benchmarks in the paper. And in this case, what we'll do is go up to the max epoch of 7, which is just an example. In this case, for the demo, it's very low. Normally, you would want like kind of much further in the number of epochs. And same here, like just trying 2 different learning rates and 2 different mini batch sizes. So we kind of select the best combination of hyperparameters in this case. And what it will return is the accuracy, the hyperparameters, and then some extra metrics, which are the precision recall and F1 score. So now that I run this, so it will actually run it on the CPU, but it will automatically detect if you have a GPU, you will be able to also run this on the GPU in order to kind of accelerate the model training. But here you see that I'm kind of iterating over the outer cross-validation and selecting the hyperparameters every time. So yeah, I encourage you to have a look at the documentation. Maybe some of you have already clicked it, but here you have the recommendation checklist, and you have instructions to install the package and also to download the datasets. That includes how to enable GPU acceleration for PyTorch, and also with the examples. So there's this example again that is in the list of examples, but also the actual example, like scripts that we've used for the benchmarks. So yeah, now it's kind of continuing to train the model. And well, we have a bit of time, so I just wanted to give a side note for people who may be interested. At the fNIRS 2024 conference in September, we will have a workshop about BenchNIRS. In order, we will kind of dive much deeper into how to build machine learning models for fNIRS using BenchNIRS. So that's a workshop that we're preparing with Borja, Jeremy, and Catherine. So if you're interested, we'll dive much more in details into how to perform machine learning with fNIRS. So you can go on the official website and kind of check the details if you're interested. Okay, so now we're coming to the last iteration. So almost there. And what it will do is essentially, by default, it will put the results in an outputs folder. So that's this folder that was created. And it's essentially saving checkpoints for the models that we've trained in order for us to, just be able to continue the training if it has been interrupted, or also just to eventually use the models in order to just make inference on new data. And it also gives you like a bunch of figures. So like here, the error across along the error with respect to the epoch number that we are at. So obviously this graph really doesn't look good because there's really too few epochs. But yeah, that's the kind of graphs that will be useful to help you developing your model. And in the end, it will also kind of show you the overall across all the testings that it has done on the outer cross-validation. It will print what is the loss and so the error and what is the accuracy in this case. And what I've done here with those two lines is first print the accuracy. So by default, the accuracy variable that I've defined here will contain 5 different values, because in this case, I'm doing 5-fold outer cross-validation for testing. And what I do here is just do the average in order to get the average accuracy. But then you could do like statistical tests with the different values you have or things like that. And just the hyperparameters that have been selected as the best ones for each iteration. And then finally, what I want to show is how can you use this to actually implement your own models? Because here so far, I've just used the default like LSTM model that we implemented for the benchmarks. But ultimately, the really usefulness of this is that you can implement your own models, and you just have to worry about the architecture of your model, and then you would kind of fine-tune it and evaluate it reliably. So here in this case, I take the example of defining a simple artificial neural network with PyTorch. So here it's very simple, just 4 layers. So the first one, for example, 400 neurons, which is the input size actually, and then a bunch, so 2 hidden layers and the out, and a bunch of hidden layers, and then the output layers, which is has the same number of nodes as the number of classes. So in this case, 3. And then I just have the forward function, which is explaining how we actually feed the examples through the model. So in this case, very simple, just using a recurrent linear unit activation function, and like everything feed forward, fully connected. So we define this architecture as ANN classifier, and that's what we can input here in the deep learn function. And again, we can define the maximum epoch and different hyperparameters that we want to select, like test, in order to perform the selection. And here I provide a different output folder for the models to put the results in. And then I can run this. And here you can actually notice that actually I've already performed the training partially. And that's why it actually kind of recovers the checkpoints in this case, and just kind of keep continuing from this point and finishing the training and hyperparameter selection. Right, so yeah, that's pretty much it. So just to conclude, so I just wanted to kind of give like small hints. For example, when reading papers, I think seeing words like cross-validation, validation, fine-tuning, or hyperparameter are significant. When reading machine learning papers with fNIRS, it's usually good words to see in a paper, and it's usually an indication that the results may be robust. And I also kind of wanted to say that when writing papers, it really helps to just report all the results, all the details, sorry, for reproducibility. So I guess the more details there is, the better, so that it makes it easier for people to kind of reproduce what you have, so that they can implement the state of the art and then build on top of that, as opposed to just every time re-implementing from scratch. And then ultimately, like, published data and code is very, very useful for people to keep building on your work. and just re-implement whatever you've done. And yeah, again, the checklist is here, so you can have a look. But a final word I wanted to say is just that, like, just to have some kind of common sense and intuition, and thinking about how your model will be like eventually deployed and used in the real world, for example, in the context of a brain-computer interface. So thinking about the ecological validity, I think that's really key to understand how you want to evaluate your models properly. So that just helps to have like a better intuition. So really thinking about down the line, what will it be used for? Right, so thank you so much for sticking with me so far. So here are the references that I've talked about, plus some additional references, which I think are must read. So the best practices for fNIRS publications, which is the best paper of the century for fNIRS. And then 2 machine learning references, which I think are very, very good. The 100-page machine learning book, which is really awesome to have basics in a very short book about anything machine learning. And finally, a very good paper by BenchNIRS about recommendations for kind of fine-tuning models, fine-tuning neural networks. So yeah, that's my contact details on my website. You can find all the informations. And yeah, I'd be very happy to take any questions or if you have any comments. Thanks.
Thank you very much, Johann, for the presentation. It's, yeah, like I said before, it's very, very nice to have this kind of research where, you know, makes the whole field more robust and better data quality in analysis. We will provide the contact details with your link there with with this webinar in our webpage. So anyone that's interested in seeing this webinar can also go and check more on your toolbox.
Yeah, so on this, I really have email and everything. So if you have any feedback about this, actually, it's really useful. Just
Perfect.
Stay in touch.
Yeah. Okay, anyone has any questions? I mean, feel free to open your mic as well now to make the questions. If no one has questions, I would just go on the others. Okay, we have one question. Do you use all HBO contrasts from each data set or handle HBO, HBR, and HBT separately? Okay. Hi, Edgar. See you're there.
Hello.
Hi, yeah, thanks. Very good question. And yeah, I mean, for the purpose of this presentation, of course, I have had to skip loads of details about the benchmarkings that I've said and pretty much doing against what I said, which is to actually describe what inputs you use. So if you have a look at the paper, there's the description, but yeah, it is in the benchmarks using both HBO and HBR at the same time for each input. Over the region of interest. So that's what we feed to the machine learning models every time. So yeah, I mean, in the benchmarks, that's really kind of, we wanted to provide baseline models in order to have a starting point. And you may realize that we have to kind of do some compromise in order to be able to compare the different data sets, the different models, and so on. So yeah, I think the hope is really to have this as a starting point so that people can eventually use it and build their own model, which I'm sure many people could could build much better models, like much more performant models. So yeah, that's a very good point.
Well, thank you for your answer and for your presentation. And if I may ask one more question about the deep architectures that you used, did you have any issues with a relatively small sample size of 20, 30 subjects?
Yeah, I mean, that can be an issue. The thing you want to do is avoid overfitting. So that's why actually in the framework, it will implement early stopping. That means that if the training performance becomes too different, like from the if you overfit the training data, so it becomes you have too much of a gap between the validation performance and the training performance, it would kind of stop the training. So yeah, that's really things to keep in mind, and that's why I think the graphs that you have are really useful for anyone developing machine learning models to have an idea as to what are your models actually doing, especially when you have small data sets. It's very important.
Thank you, Johann.
Thanks.
Thank you. We have another question. First, thank you for the great presentation. The FIDSA wants to know how reliable is the BenchNIRS as a validation methods. Do you know other researchers using this already?
Yeah, no, very good point. So yeah, I mean, the goal is really to make it open source so that anyone can use it, anyone can give feedback, and hopefully help make it better. Because that's really the idea, to kind of build together like something that is just better and easier to use. In terms of like the actual approach, so nested cross-validation is really something that is used, reused in many different fields. So that's really something that is very robust in order to like fine-tune models and evaluate them in a reliable way. But yeah, that's a very good point.
Thank you. Any other questions from the audience? Okay, there are a couple of questions that people asked before, and I will address some of them. First, does BenchNIRS take into account different pre-processing steps? I guess.
Yeah, so there's different things you can do directly from the framework. So as I've shown in the example, for example, filtering or motion artifact correction. There is not everything, but using MNE, actually, you can implement loads more. So yeah, if you have a look at the MNE documentation, you may see like tremendous amount of different signal processing that you can use. So as long as you've loaded the data as an MNE object, then you can do any signal processing, and then you would be able to use one of the BenchNIRS function to convert that MNE object into something that you can use for the model training.
Okay. Just came in another question. Thank you for the presentation again. Typically, deep learning algorithm provides better accuracy, but you showed LDA in your research perform better. Do you have any specific reason about that? Or
well, yeah, I don't have that much explanation. I think one big thing is that LDA, for example, has much less hyperparameters than deep learning architectures, for example. So it actually makes it much harder to actually have this optimization leakage, which is selecting hyperparameters on the test set, for example. So in this case, there's not much you can do. But yeah, that's a very good question. I think one of the big issues is how to reproduce other like deep learning models. I mean, we need to kind of start somewhere to kind of implement the thing and share how we implemented it in order for us to really compare. But yeah, I mean, I think also deep learning models, they can be so complex that it's hard to say like this model is not working, because there's pretty much like an infinity of architectures that you can try. So obviously, yeah, that's why it's also good to have to share the results, so that maybe someone else may find that it will work much better. And I'm very sure this could happen. So yeah.
I don't remember much of your data. If you could put that, you know, the table that you have with everything, but inside of the motor package, the motor data set, was that different?
Yeah.
The accuracy from LDA to the others? You know, considering just that data set.
Yeah. So yeah, because keep in mind, so those three first ones are three classes. So yeah, chance level in this case, because all the classes are balanced in this case.
Yeah.
So that's
So
33% as opposed to the other ones. But here it's reaching much higher than the other ones in this case.
exactly. So the LDA inside of the same data set, so to say, that were already expecting much better accuracy than the others, it's not actually. So it's also, you know, it's in line with what he's saying here. If you have a good data set that you can discriminate, then maybe others would be actually higher than the LDA. That's an interesting question, though. Thank you.
Yeah, I think I was watching a presentation by Christian Herf, who's also like a great researcher, and he was also saying that he's always using LDA first, because yeah, I think that's a very simple model that, I mean, yeah, it's a good starting point with machine learning, as opposed to implementing very complex deep learning models. Yeah, it's a good thing to try first.
Indeed. What do we have here? On the timing, that's also we were asked here, you know, to do all this K cross validation, nested validation, how long usually it takes one of those analysis? Well,
yeah,
if you could just.
Well, it depends how many tests you run. So we've reported the training times for running all the benchmarks in the paper, I believe. So yeah, I mean, the more you will test stuff, the more it will take time. So I mean, for example, just an idea in our case, in the benchmarking of all the models on all the data sets for the unseen subject classification, if I recall well, it was taking like 24 hours roughly to run all those with like hyperparameter selection and cross-validation and so on. I guess a more traditional, like a more typical case in which you may use this is just you want to develop your own like model, like for example, a new neural network on one of the data sets, and you want to say, is it better than that other work? So in this case, of course, it will be much faster, but yes, it does make it longer, but it also makes it much more reliable.
Yeah, indeed. Should not, if you're evaluating your own model, especially, you should definitely check.
Yeah, also one thing I wanted to say is this will also work if you run it on remote computers. So for example, we've been using the high performance computing clusters. Can run it like on remote computers. They run and yeah.
Hey, do we have any other questions? No. Okay, I think that's it then. Johann, thank you very much for coming and showing your work. This webinar will be provided the recording as well. Yeah, you want to say
thank you so much. Yeah, I mean, yeah, thank you so much everyone for joining. If you have any feedback, please do contact us. We're very happy to have any feedback about this. But thank you for the opportunity.
Pleasure to have you here, and we meet at fNIRS. Yeah. Thank you very much, everyone. Until the next webinar. Bye-bye.
Bye.